continue where we ended with the stabilizer formalism, and we'll discuss a couple of typical techniques for modeling error correcting codes and for creating error correcting codes. And yeah, that's it.
Okay, I was planning to start at like 5 minutes after anyway. I'm definitely about to poke myself in the eye with this. Okay, so as Stefan mentioned, we're going to be doing some intro to GPU stuff today. So the way I've set this up, hopefully it won't require you to have a GPU on your laptop or on some clusters. So I tried this at like 1 p.m. today and it worked, which definitely means it's going to explode now. So hopefully it works. So I'll paste some links into the Zulip. Give me 1 sec here. So we're going to be using Google Colab for the notebook today. So who here has used Colab before? Quite a few. Okay. Who here has used a GPU on Google Colab before? Some? Okay. Okay. Fewer, but still pretty good, about half. So I might also have to lean on you folks again. And I also need to share my screen. That would probably be helpful. So Colab is going to give us access to a pretty crappy NVIDIA GPU, but crucially, like more or less for free for 30 minutes or so at a time. That should let us go through most of the basics, and then you can keep working on your own if you're interested. So this is going to be a pretty like high-level introductory overview. So I guess while I wait for people to open this up, you'll need to sign in with your Google account. Hopefully everyone has one. I'm sorry if anyone here is like the world's biggest Google hater.
Not Google.
Oh, yeah, there's a question in the back.
Quick, I do have a GPU. Can you tell me like, can I just do it on normal?
Yes, so if you have a GPU, a CUDA GPU on your laptop, you can just run the notebook I'm going to send in a moment, like in a Jupyter server on your laptop.
Okay.
Because the GPUs we have through Colab are kind of crappy, as I said. And also, I'm aware that this is really dark right now, so hopefully I can like zoom this in and make it a little bigger. Yeah, we can turn on the lights. Better? And for those in the back of the room, is the font size good? Okay, thank you. Okay. And then the notebook we're going to be working on has a really exciting name. So if you open up Colab, it should... Can I open this next tab without like closing my own? So if we open a notebook, you can go to GitHub, enter a GitHub URL or search by organization, blah, 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 blah. And if you just paste in the IPyNB, I just linked in Zulip. Again, this worked earlier this morning, but hopefully you see something like this.
Where do you paste it again? I'm sorry.
So if you go to File, Open Notebook, and then there's a GitHub option. So I'll leave this up for a second. Now it's like spying on all my repos, but okay. While I do that, it's time for another poll. Who here has written some CUDA code before? Quite a few people. Who here is aware of CUDA but has never written any code that actually calls it? More people. Okay, great. So hopefully it'll still be accessible to a lot of people and you won't be completely bored. And final polling question, I guess, while we get this set up. Who is like kind of tired? Or okay, you can kind of or more. We'll put the floor at kind of. But you can be very tired and say yes to the question. Okay, so I'll try and keep this relatively brief. Ideally, we won't be here till 10:30. I mean, if you want to chat until 10:30, you're certainly welcome to, and I'm happy to stay and do that, but I'll try and keep the lecture shorter so that if you're sick of listening to lectures after, I think, like 25 hours of lectures in the past 3 days, then you can just like dip and go lie down. Okay, so has everybody managed to get to this? Yes. Okay. Next item, we need to make sure that we're going to connect to the correct runtime. So we need a Julia runtime that has a GPU available. If I save this correctly, this should just work. But again, So does anybody not see that little T4 in there up right here? Since I clicked connect, mine already went through. And if you click connect, which you should do now, you should see something like RAM and this little disk icon. I'll try and like make it bigger. Oh my God.
T4.
The font size is so, yeah, you want T4. So that is a Colab instance with access to a CUDA GPU. And again, if you have a NVIDIA GPU on your laptop, you don't have to do this, but I assume you know what you're doing setting up Jupyter.
I can tell you mean by T4.
Go here.
I think I opened the notebook right, but because I tried doing I tried uploading it to the GitHub notebook, but I just,
Okay. Is anybody else not connected? Okay. I'm going to zoom out just a little bit so the font size isn't humongous. Okay, so there's sort of two parts to this notebook. First, we're going to talk about the CUDA.jl package and use it to illustrate some of the basics of GPU programming. Part of the reason for this is that it's the most mature GPU framework in Julia, and it's also the one I'm most familiar with because I've worked with it for like about 10 years, which is also crazy to think about. So I guess for any of you who are like, have used CUDA before, my first CUDA version was 3, and now we're on, I think, like 13. So it's been a lot of CUDA versions. And this thing will allow us to use the GPU for about 12 hours of interactive experimentation. Hopefully you don't stay up till like 8 in the morning. But if you're inactive for 30 minutes, you'll have to reconnect. So just keep that in mind. And as we'll discuss a little bit later, if you're like me and you have a MacBook, especially a newer one, you might already have access to Apple's Metal, which is another GPU programming library. If you have AMD hardware, like if you bought one of their gaming GPUs, you might be able to use ROCm on it. So we'll discuss how to use different vendor libraries later. But for now, for illustrative purposes, I feel like this chair is going to kill me in a second. We're just going to use CUDA. So this is NVIDIA's sort of extension originally to C and C++ that lets you program graphics hardware using some additional features of either the C or C++ programming language. And now we have Julia functionality built on top of this. So CUDA itself is actually made up of a few different components. There's the GPU driver. So, okay, I feel like I'm really taking a big risk here. So who here, and I mean this in a good way, who here is like a gamer? Damn, like 3 people?
Somebody's not raising their hand.
Yeah, okay. So if you know, if you're one of those poor benighted souls and you have to update your GPU driver, CUDA or NVIDIA usually ships a different version that's specifically optimized for computation. So this driver controls at a low level the actual graphics card hardware and the interactions it has with the operating system kernel. So this is also what gets you things like monitoring the temperature of the device, and like really basic, like if you wanted to render graphics with your graphics card, which is kind of a crazy thing to do, but apparently some people want to do that. Clearly not many in this room because there's actually not that many gamers. Then on top of that, you have the CUDA runtime, which provides these basic language extensions to C, and the basic CUDA API for sort of actually programmatically controlling the device, and the CUDA compiler that takes your C code and boils it down now through LLVM to the instructions that the GPU can actually handle on its own. And then finally, it ships the CUDA libraries, which provide a GPU-friendly or GPU-accelerated implementation of a lot of stuff we use day to day. So a lot of the linear algebra routines we use very frequently, like in BLOS. These guys all have really creative names. They just put Q in front of them. NVIDIA loves this naming format, and AMD has a very similar one. They have functions for doing on-GPU random number generation and lots of other stuff, including like sparse. So one thing that's really nice about the CUDA.jl ecosystem is that it has prepackaged stuff for all of this. And if you run package add CUDA for the first time, everything should just work, and you should just download the most recent CUDA that's supported on your hardware and your OS. And if you've ever had to install CUDA for like PyTorch or something, you know how insanely painful that process. There's like a bunch of people shaking their heads in the back. So one thing that's really nice about using this from Julia, again, if you've had to program CUDA or any GPU library in C, is that a lot of the constructs are very similar. So for example, we can just like create a random array with syntax that's pretty similar to what we're used to. So I just call this function CUDA.rand for a float64 and I make this big chunky array. Okay. But already we can see if I just look at its type that something is different. So this isn't a regular array type. It's not your granddad's array type. It's a Q matrix or a CuArray of dimension 2. And it now has 3 type parameters where normally matrices only have 2. So the third one here is some weird guy called CUDA_device_memory. And so this is kind of my first off-ramp to try and draw stuff, which is going to be really exciting. So why does this have a 3rd type parameter? Well, so here I guess we can get to like a little bit of the theory part. I don't know which color I want. I'm really sorry. So when we think of like GPU programming, if we actually sort of draw a cartoon of what our computer looks like, I'm going to try and draw this really big. Because I drew stuff way too small the other day. And by really big, apparently, I mean like the size of 2 sheets of paper, but okay. So in a modern, like, let's see if my laptop had a better GPU than it does, I have a couple CPU cores here. I'll draw them in blue because it's friendly. And I guess we'll pretend my laptop is worse than it is because I only have 4 cores here. And then these guys have their own RAM pretty close to them. So actually, like all the array programming we've done so far in Julia, unless you created an array that's really, really big, all those little arrays we were dealing with are living in this, usually in the CPU RAM, and then the CPUs check, hey, where's this memory? And they do operations on it. Awesome. And we don't even have to think about this. This is all handled for us by the operating system kernel, and we just program away and we're super happy and we love life, ideally. So what is different with the GPU is that now we have an additional, what people call like a coprocessor, which lives over here. And again, this is a cartoon. So from the point of the CPU, or the CPUs, actually, let's pretend I have a really nice computer and I got 2 of them. Just because I drew this in kind of a funny way. So these are effectively sort of, what's that sort of says? They're sort of remote assistants. So these have their own on-device RAM, and we'll get into some of the more subtle aspects of this. So these have completely separate memory from this, and they are effectively schedulable assistants. What do I mean by that? So is Stefan still in here? No, Lucas is though. So I won't tell you Lucas's phone number, but effectively the relationship between the CPU and the GPU is let's pretend I'm the CPU, I'm doing some work, and I'm like, you know what? I have an operation here that I am just too slow to figure out. So in my case, that's because I'm just kind of dumb. And in the CPU case, it's because there's certain operations that this object is going to be much better at. So what I do is I asynchronously call Lucas. So I send some instructions over here, or maybe some memory. Some work happens, and then Lucas at some later point, perhaps much later, phones me back and says, hey, I finished the work. Or more likely, hey, the work you sent me made no sense. I erred. So after some time, results come back. So the entire programming model for these GPUs is asynchronous. And I guess you kind of hit the limits of the phoning your buddy analogy. But the idea here is that we have some resources that are sort of in the same box, but we're controlling them in a way where we send tasks and then at some point later we get results back. And we can choose to wait on those kind of events. But the programming model is pretty different to maybe the one we're used to, and this introduces a lot of complications, which we'll talk about. Okay, so if you're unfamiliar with GPU programming, you might look at this and say, like, this sounds like a huge pain in the butt. I don't want to do this. Why would anyone do this? Well, so as the name kind of implies, the G in GPU stands for graphics. So these were originally developed for the purpose of rendering images like on your monitors is happening right now. So I have like an integrated GPU that is currently rendering this. And one aspect of that is that for every single pixel that needs to be drawn on this screen, we can do a large series of matrix multiplications to figure out exactly like what color the pixel should be, how bright should it be. I guess those are basically the three things we control. So there's 4 numbers. And so all of the graphics rendering pipeline that like it comes through for here, or for something more complex, like rendering a scene in a movie or like in a video game you're playing, is effectively a large series of matrix multiplications. And some very insane person in the late 90s realized that you could allow people who were equally insane to control the programming pipeline for a large series of matrix multiplications and control the GPU and let them multiply their own matrices that are totally unrelated to drawing a picture. So these red hardwares are like in a way very specialized, and they're really, really good at anything that looks like a matrix multiplication or a couple other operations like adding 2 vectors together. People usually call these like embarrassingly parallel operations, which is a term of art. And I actually am I had somebody complain that this like wasn't a professional term. They were like, you have to take that off a slide. And it's like, no, that's what they call it in the textbooks. It's called embarrassingly parallel. So if we actually like sort of zoom in on these guys, I'm kind of running out of room already. So what is it about these that makes them really good at doing this? Okay. So if we think about doing a matrix multiplication, I'm actually going to go over here so I don't completely run out of room. And I am not going to trip on your power cable. Okay. So if we're multiplying 2 matrices, A and B, I'm like a serious risk of killing myself right here. Okay. So I'm not going to write down the whole formula for this, don't worry. This is, if we think about it, like normally if you're in linear algebra 101, of course you do this in a step-by-step process because you're a human being and you're trying to make sure that you fill in the output row like 1, 3 correctly. But if we think about it, this process can be parallelized because we know the output for a certain element here is the result of multiplying this row in A. I don't want to color it in, I'm lazy. By a certain column in B. Okay. So if I do the subcomponent of the problem like this, then I get a 1 single element out for the output matrix. And you can run every single combination of rows and columns in parallel, and in fact there's better than that we can do. But effectively, for this reason, the architecture of the GPU is super specialized to be really good at doing problems that you can write in this sort of formalism where you have some extremely parallelizable problem, which I hope makes sense. So the drawback of that is that because these are extremely good at doing matrix multiplication, that there's many things that they're bad at, which we'll get to. But I just wanted to motivate a little bit, like, why does anybody care about this in the first place? Why do I have to hear about this? So from the physics point of view, happily for us, there's lots of problems that can be written in a way that are embarrassingly parallel. So a really obvious, maybe example is doing Monte Carlo simulations. You can just kick off like 200,000 trajectories, and they mostly don't interact with each other. That cannot be true if you're doing like parallel tempering or something like that, but in general, it's an embarrassingly parallel problem. Obviously, there's a lot of physics problems, like for example, that we saw earlier this week, that you can just write as this over and over again. And there's also other examples would be like finite element methods, if anybody's done any PDE solving. I'm trying to think of other things. There's a lot of like, so yeah, like sort of mesh-based methods as well. But effectively anything that you can sort of, if you squint and look at it a little funny, you can say like, there's a bunch of extremely large number of independent operations that are effectively very similar to one another, then great. You can use the GPU and it'll be effective. And the reason people put up with this also is that when we say effective, the GPU can be something like 10,000 times faster, depending on like in the best case. So for example, like this is also why if you hear about, like all of these data centers that people are building for the ML inference tasks, the reason that they're willing to spend $1 bajillion, very technical number, for the NVIDIA H100 GPU is because it's massively more effective for this, especially on the data sizes that they're dealing with. And for that reason, I guess it's worth it to them. And also the entire like feed forward process in the neural net is just matrix multiplication. Partly it's also a fact, I guess I'm not like an ML researcher, so don't, like try and take this to the bank or anything. But the fact that the GPU is really, really good at matrix multiplication also kind of biases people towards stuff that's expressible as matrix multiplication, because like we know we're really good at that. Okay, so this very long digression is all to say that when I create this array, this CuArray float 32 that lives in device memory, what that's saying is that this, my beautiful little array I created, is here. So, and so the way we interact with it is going to be a little bit different than the way we normally interact with arrays that live here. So, okay. So when we say that the CUDA array lives in device memory, we specifically mean that only instructions that are executing on the GPU can access it. This is like a 50,000 foot description, but for now, that's more or less accurate. So for example, one thing that's kind of strange is that we can't actually access individual elements of this array from the sort of regular like REPL or CPU-based side. The only way for now that we can talk to this thing is with what we would call like collective operations. So some function that runs on every single element of the array. And as an example here, I have my map operation, and I realized I didn't actually run all of my, yeah, okay, it's not authored by Google. That would be strange if it were. So I'll start running my cells here, which I forgot to do earlier. Sorry. So an operation like this that just squares every element is totally fine because it's applied to a collective, either like the entire array or some large subsection of it. So even if I had done something like, like 1 to 1024, that would also be fine because I'm operating on a chunk of the array. But what is not allowed is to operate on like this. I mean, that would be kind of weird. Why would you use map there? But so already starting out, we have to think of how we can express all the operations we want to do on these device arrays in a way that is like sort of collective. So if you're coming maybe from more of a functional programming background, I think Ray on Monday, which might as well be like 1,000 years ago, asked how many people had functional programming experience. This might feel a little bit more natural to you, maybe. But we need to see if we can express everything we want to do using these operations like map, map reduce, sum, things like that. So one thing also that's really nice is that when we instantiate this array, Julia just creates it on the GPU memory for us. And then we might also remember, like from the Halcyon days of 5 years ago. Oh, there's a question.
Sorry to interrupt, but I keep getting a CUDA runtime not found issue.
You're the person who has a GPU on your laptop, right?
Yes.
Okay, I would suggest
Just go to Colab?
I would try Colab. Sorry.
Yeah.
So we know that Julia is a garbage collected language, and one really nice thing about using any of these GPU frameworks from Julia is that the garbage collector is actually extended to work on the hardware for us. So again, for like the 3 people here who've used CUDA-C, you'll probably remember that having to create and manage arrays that are not in CPU memory can be really, really frustrating, let's say. You have like pointers to pointers to pointers. It's not great. Yeah, I see someone else in there has been traumatized like me.
Yeah.
So Julia will just create a pool of memory that it manages and then allocate and delete arrays for us as needed. And one thing that's also quite nice is it actually creates like, sorry, this chair keeps moving. It creates pool of effectively like the largest array we've ever allocated so that subsequent allocations are really fast. And you can turn this off if you need. But I've allocated some, I guess, reasonably sized array, 10 to the 24 by 10 to the 24. And so I can just check and say, hey, CUDA.jl, how much memory do I have available and how much have I used? So I can just check the pool status, and I can see that my effective GPU memory usage is less than 1%. That's pretty good. I guess they made the GPUs that are available better because I remember that they were substantially smaller than those. And the total memory pool has used only 16 megabytes, which also pretty good. So this function can be used to just give you a heads up if you're running out of memory or if you need to invoke the GC earlier. But it's just kind of a nice example of how Julia makes doing this a lot more convenient than it might otherwise be. And then we can allocate another very similar device array. I wasn't really super creative when I did this. Sorry about that. And again, I engage in some collective operation to make it actually, it's a real, so it's also symmetric, but this would make it Hermitian. So I do a broadcasted add to just add its Hermitian conjugate. I check the pool status. And we see that the memory pool usage has doubled, which makes sense because I now have an array that's twice the size. But the effective GPU memory usage has not gone up because when I started CUDA.jl, it already made a relatively large pool for me. And the nice thing about this is that we should never need to explicitly deallocate the CUDA arrays. So you never need to really call free. You can give CUDA hints that you're done with an array, which can help if you need to reduce memory pressure. But in general, for most use cases, you won't need to do this. So the reason this matters is that I guess on my laptop here, I have 100 something gigabytes of RAM, which is a reasonable amount for a laptop. On a cluster, you would usually have substantially more. But even pretty expensive GPUs you have access to have much less RAM than the main CPU pool of RAM. So a lot of the challenge we're going to have programming these devices is we have to be careful about how much memory we try and squeeze stuff into in order for us to actually be able to get the work we need done. And also, yeah, just a note, if you unsafe freeze something, I guess this should be obvious from the name, but once you've unsafe freed something, you can't then go look at it later. That's very dangerous. You will blow up the entire program and you'll probably segfault. So just as an illustrative case, if I unsafe free my memory, then I see that the pool usage has gone down. Okay, great. So one thing that's also really nice about programming this hardware in Julia is that we actually have a lot of higher level array operations already implemented, a lot of map and broadcast based stuff. So for many situations, you can just use these built-in primitives and you don't need to worry about managing the memory or writing super performant functions or anything like that. It just works. And one thing also that we should, I guess, cover now is that when we send work to be done on this GPU, so with my analogy of I'm really stupid and I call my friend Lucas and I'm like, hey, you're smart, can you do some work for me? There's always some latency, so some delay when I send some work to be done. Like this. Again, in the phone analogy, I gotta wait for the phone to ring and then Lucas picks up and then I have to actually describe to him what my problem is and more or less what I want done. So to even get work started on the accelerated helper here, there's already a pretty large latency, about often 40 microseconds or something. And that's the case for every single independent operation that I start here. So for example, one single call of map on my array just has a 40 microsecond startup time. So if the total time to do the map is much less than 40 microseconds, then I didn't really save myself anything. And if I have 10,000 arrays and I call 10,000 maps, and each one of them takes less than 40 microseconds, then I'm really slowing myself down. So another thing we're going to have to worry about is how can we pack things together so that instead of sending a lot of really small function implications, I send a small number of really large ones. So again, in my phone analogy, that would be if I called Lucas just once and I was like, okay, I need you to do this, and then I need you to do this, and then also this, and then probably he hangs up on me. Sorry?
Can confirm.
Yeah.
We'll hang up.
I mean, well, at this point, you're probably seeing my name on caller ID, and you're just like, nope. But just for the purpose of the analogy. So, for example, doing something like a broadcast over each column will usually be much slower than doing a product over the second dimension. And the reason is that this is one single call, so one single like 40 microsecond latency launch versus for something like this will launch a separate instance of broadcast for every single column in my array. So in the case of the arrays I showed earlier, this you could expect would probably be like not 1,024 times slower, but substantially slower. And part of the reason for this is that CUDA.jl has a lot of functionality, and so do all of our GPU packages, but it isn't what we call like a tensor compiler, so it's not smart enough to notice you're doing something like this and say, hey, wouldn't it be a lot smarter for you to do this? So it gives us a lot of powerful functionality, but it can't necessarily protect us from doing something foolish. One other thing that's really nice, as I mentioned earlier, is that we have a lot of these array features that we've covered in previous days, and they just work on these GPU arrays. So almost all of the GPU vendors provide a BLAS-like library. In the case of NVIDIA, it's cuBLAS. In the case of AMD, it's RockBLAS. And we can just use these basically as drop-in replacements for the existing linear algebra code we already had. And that's great because for a lot of the operations we need, like our beloved matmul over there, we can just instantly see a speed up from pulling in these libraries. So here, I'm just showing an example where I turned on the logger. Normally you would never do this. I just turned it on so you can see like, hey, this is actually being used. And then I just multiply two arrays together. This is again matmul that we know and love. Then this dumps out a bunch of stuff that's like not particularly interesting. The main thing is just to show that cuBLAS is indeed being called. And so just by calling like the regular multiply operation on two CUDA arrays, Julia automatically sends this to the super optimized NVIDIA cuBLAS wrapper, which is pretty cool. So you don't really have to modify your code that much for this linear algebra stuff once you've made sure that everything is a CUDA array, which is, I think, pretty cool. And you can even do stuff like factorize a CUDA array into QR format, and it just comes out as like the QR after calling the sort of internal CUDA QR factorization, which I also think is like quite cool. And again, works reasonably well. One thing that's also pretty cool about these devices and the programming framework is that earlier we created a matrix that's 1024 by 1024, which is reasonably sized, but actually from the point of the GPU, not super big. So if we zoomed in again, I'm gonna have to draw more, I'm really sorry. This hardware has in it. So here I drew like 4 CPU cores, which I guess is like on a reasonable laptop. And as mentioned earlier, like some HPC node might have like 192 CPUs, I guess. But on the GPU, I'm not going to try and draw all these also because I'll lose count. But you have, I'm just going to draw them as dots because it's easier than me trying to draw squares. You have many thousand of what are called these streaming multiprocessors. Kind of screwed myself over here with the way I did this. So there's many, many thousands of these. And when I actually launch this matrix multiplication operation with my relatively small matrix, some number of these streaming multiprocessors are actively working on this at one time. The way I drew this is kind of suggestive because a large number of these streaming MPs are idle with a relatively small problem like that. And one thing that's quite nice about the GPU programming model, which is asynchronous, is that I can effectively set up a really large pipeline of stuff I want it to do. So I can say like, okay, I have 5,000 of these matrix multiplications. I don't care what order you actually run them in, but just do all this stuff and let me know when you're done. And what the CUDA driver will do is it will then start scheduling. I'm going to run out of colors here. it'll start scheduling these, and as these streaming multiprocessors become available, it'll just assign chunks of them to do the work as it goes. And so you can actually have multiple functions executing, or multiple kernels as we call them, executing simultaneously on one GPU, working on different pieces of hardware. So this is, again, also, I guess, why it's very effective for the machine learning application. And so here's just another quick example of how we can do this and how like the programming model is a little bit different. This example is pretty contrived. You wouldn't actually do this in real life, but it's just to illustrate that you can effectively set up a really big pipeline of these functions that just execute on the GPU, and when it's done, it lets you know. So we create, oh, there's a question.
Yeah, you mentioned that 1024 isn't big enough to saturate most modern GPUs. At what size of matrix does the GPU sort of start to struggle, or is it actually sort of saturating it? Just to like get a feel.
It really depends on the GPU. It also depends on how much RAM you have, right? Because this one is 16 gigs, so you could, like, if you had two matrices, each size, like, it also actually depends on the element type, right?
Let's say like real matrices, real floating point 32-ish.
I mean, I think in most of their benchmarks, they do like 64,000 by 64,000. Like, it also kind of depends, because if you want to run these in parallel, you can saturate the whole device with these 10 by 20, 10 to the 20, sorry, 1024 by 10 to the 24, if you have a lot of them.
Yep.
So yeah, the answer is it depends. Oh, there's another question.
Yeah. How safe is it to play around with this stuff, like put 1 million in here and stuff and see what happens?
So if you try and put like 1 million in, I think you should just get an out of memory error, and it should be fine. But yes, you can definitely set it. I set it to 1024 to be safe, because again, last time I was doing this, the GPU I had access to was worse, but you can definitely play with it. So just as an example, I just create 100 arrays. I copy them to the device, and then I run a MapReduce on every single array and store the output in some CPU-based results array. One thing that's also pretty cool about the way Julia handles this is that if I'm using Julia threads, they'll handle running these functions asynchronously in parallel on the GPU for me. So each of these spawns says, okay, like create a separate a kernel launch on the GPU. They're waiting in some queue, and it'll just start picking out chunks of work independently and in parallel from this number of arrays of threads. And then when everything is done, the sink on the outside says, okay, like just wait until this whole interior block is finished and all of the work is done. So if we removed this sink on the outside, which stands for synchronize, then this would actually just return immediately. And then at some point later, we could go to the washroom and like come back. And then when we come back, we could say, hey, are you done? And if the device is done, okay, great. Or if not, we could wait. And with that, it's been like 45 minutes. So why don't we take a 5-minute washroom/water break? Or just like hang out. And we can come back at 8:20. Does that sound good?
Yeah.
Okay. Yeah, I realized like before we were going like for hours with no breaks. This is kind of crazy.
They're trying to print out the result.
On somewhere with a purpose. So
Back to the
just put your watch for a purpose.
Oh, we discussed.
Okay, I'm also gonna go get more water actually. But you have a question first. Sure, yeah. I'm just trying. I'm like so frightened of tripping on a cable.
It's Windows or?
Yeah.
Yeah, so I think it's easier with Windows. It's on drivers.
For some reason, when I tried to do it on like a separate project, it's
When I stay.
That was what he said.
I'm not sure it's called that.
Really?
Also, you know what? There's also something called library version of Julia, and it's compatible. They also need to be compatible with. Yeah,
The documentation says it should take care of it on its own.
Oh.
The Julia documentation.
They automatically install.
Oh, sorry, Jesus.
It automatically takes care of the CUDA.
Yeah, for your C++,
Yeah, so
you need to do by yourself.
so all I had to yeah, see, so all I had to do was add CUDA.
We just play card games on
Which runtime you use?
Oh,
Latest version. 813. Yeah.
23.
in the office.
Yeah, no, 13. V13.
Oh.
3.
Yeah.
Yeah. So.
Okay, you got to keep that back. Yeah, okay, understandable.
So this small monster has the GPU?
That is scary.
Also scroll. Okay, now I got it. What's designed for
See something starts laughing.
Adobe Illustrator?
Yeah, so and they are telling you going like, dude, we should rent a car.
I don't know what I'm doing at this point.
Go where?
If it's rotating, I don't want to go, like, yeah, it's hard, you know.
Rent a car. You don't rent a car.
Go where? Canada, go where? What do you want to do? No.
Yeah.
We can go, maybe.
I studied all the
Yeah, he's already knows about that.
Are we talking like this kind of thing or what?
He is the center.
Nice pickup.
But I guess how many?
Yeah, how's dinner?
Yeah, but
I was pretty full.
Yeah, it's easy. So I think maybe a perfect average or that's 3 days.
good to you.
And thanks for getting the bagel.
Yeah, overall it was fun.
Yeah.
Maybe that's a really good idea. So.
I think minimum wage.
Oh.
Oh, I only skipped one.
You gotta hand in your,
I think maybe I can start it just because of that.
Yeah.
I think,
I mean, I don't know. It might be good.
Yeah.
Oh, nice. Oh, shit. Yeah, so then I'll save another one here.
No, I already have.
Versions of CUDA, PyTorch, try to make
I have
it
plenty extra ones. I
together.
skip like 2.
It's really a big pain.
3 of them.
It's really big.
Did you have breakfast today?
Like, why you want how good isn't to use
I think I skipped dinner and I skipped breakfast.
Yeah.
You need to skip.
Hey.
Oh, it was like 1 hour.
Vector that we were calculating in the
I
last
could probably
example.
skip one and then.
And it was pretty funny because it was all
I should skip
zeros.
today, but I'll be alright.
You have an insight on that?
This one you mean?
Yeah.
Hold on.
Like if you try to print results, any indices.
Oh, no, I think I.
Oh, yeah, that is crazy.
It was like,
Yeah,
there is some
there's something going on there.
approximation.
Yeah, I think what's probably going on is like it's generating really large random numbers and then multiplying them, and then yeah, the sign is just like
Because the randa is.
Yeah, because that's
that's right.
Yeah, I was like,
different kind of vocals.
yeah, very, very different.
Yeah.
9 gag.
This is all like,
Yeah,
exactly. Yeah.
every day.
And the other thing that is going to figure out is when are the CPU instructions sent to the GPU? It's like use QuArray being sent.
Yeah, I wonder if that might be why. I might have. Again, this worked. Yeah, sure.
It's
Yeah, well, it works, right?
Like, it was
Just
like, there was like.
Yeah, it also could. I don't know. There's it was not doing this earlier today, so I really wonder what's
I
going
was
on.
using here. I tried to change the multiplication to plus, and it does work. Maybe
That also could be, it could be just be like a really old card or something. Yeah, indeed. I don't know. I think it might be just be like having overflow or something like that. Yeah. Yeah, it's like an illustrative example, so hopefully nobody else worries about it too much. Yeah, that's quite strange though, eh? Yeah.
I was like, maybe there is a programmability argument that if you take a million floats, at least one of them is close enough to zero.
Yeah, I think that's probably what it. Yeah, for the times, that's probably what it is.
Multiplying with it.
Yeah. Okay, I think it's 8:20. Sorry, I don't mean to cut you off. Sorry, no, you can come back. You can come back. We're summoning people. Okay. So we'll just keep rolling. So this example we had here is like obviously like this is a little stupid. I mean, you probably wouldn't do this in real life, but the main point is just that you are able to even like parallelize across function invocations as long as you're sure they don't interact with each other. So indeed, if you're in this situation like I just made up here, like you have a bunch of these really small matrices, but they can be run independently. This can allow you to saturate the GPU by launching different functions and to run in parallel. So again, this would be like a good example. If you were running multiple independent Monte Carlo simulations, you could just completely saturate the GPU if you use this sort of like threading based approach. So it's a nice little pattern. And one thing that's also really nice is that cuBLAS and I think some of the other linear algebra libraries like for sparse knowledge also provide what are called batched versions of some of these common functions. So in this specific example, like if I had 1,000 matrices of the same size and I wanted to multiply them by another 1,000 matrices of the same size, you can do that in one fell swoop with one call to cuBLAS. So there's like effectively very little overhead from launching the kernel, and then CUDA internally handles scheduling all of this on the device for you. They add this sort of stuff as convenience features when enough people complain that like their kernels are not very effective. So I guess that's also a good introduction to another feature of GPU programming, which is the only way to get features added is to complain really loudly. I mean, maybe that's true of all programming, but I feel like it's especially true here. So one thing we should also keep in mind in an example like this, where we're transferring a lot of memory back and forth, is that even copying memory back and forth from the CPU RAM to GPU RAM is really high latency. You're probably noticing a theme here, which is that getting the GPU to do anything is really high latency. So we need to think carefully about the layout of what we're transferring and the order in which we transfer stuff. And the upshot of the high latency issue is that it's usually better to copy one really big object than to do small copies of many copies of really small objects. So for example, if you have a bunch of small arrays, it can make sense to sort of splat them together into one really big blob. Of course, keeping track of who got smushed into what, and then copy that big blob to the GPU memory. And then use that accounting you did to do useful work on it, rather than copy all the elements individually.
Could you copy like whole libraries? Or data stores or whatever?
Yeah, I mean, you can copy like effectively like an opaque blob of stuff. You just need to know on the CUDA side like how to operate on it. I mean, from CUDA's point of view, like actually under the hood, what's going on here is that like there's a pointer and a size of. So as long as you're consistent about that and you know how to index into this thing, like it doesn't care. But you have to be a little bit careful, or you have to tell Julia how to be careful about like how this works. So we won't go into it as much, but you can even like have like Julia structs that live entirely on the GPU, as long as you're consistent about it. And there's some restrictions there. We can talk about that a little bit later. And finally, I can answer the question that I posed earlier. What the hell is that device memory thing? So by default, these CUDA arrays, and this is indeed true for AMD as well, live in the GPU memory, and they're really antisocial. So they can't be directly accessed element-wise from the CPU side. This is for efficiency reasons, because effectively to access a single element of the GPU array, you would have to copy it back. This is A, high latency, and B, slow. So if you try and go through each individual element of this, you'll be wasting a huge amount of your time. However, one option to get around this, which we won't go into super detail here, but I just mentioned it so you know what it is. They also have this paradigm called unified memory, where the GPU array is now fully visible from the CPU side, and CUDA's driver handles doing the transfers back and forth for you. So this can be really useful, for example, if you are like on a high memory node, and you have a terabyte of CPU RAM and the GPU only has 80 gigabytes of memory. So you have some like mega array, again, very technical term, that fits like just barely in the 1 terabyte memory of the CPU RAM. And you don't want to have to deal with slicing and dicing this guy to get it onto the GPU in sizes that fit. So if you declare it unified memory, both sides can see it. And then as you access portions of it from the GPU or the CPU, CUDA's driver will handle doing the copies back and forth for you. So what's great about this is that, I mean, yeah, you don't have to worry about it. Sounds pretty attractive. The downside is that you have like somewhat less fine-tuned control about how exactly copies are happening. So there can be sort of intermittent latency and things like that. A lot of really smart people work on this, so generally the performance is really good. But if you're an expert who understands the sort of memory needs of your program, you can often do a bit better just because you have the actual domain knowledge. So I guess also if you're dealing with these CUDA programs, you're like, this is so horrible, I don't want to deal with transferring arrays back and forth, the unified memory is a good option, and we support it basically natively, I think, in CUDA.jl. And one other thing you can do, if you have some big CPU array that you know you'll be needing a lot, is you can actually do this thing called pin. This effectively sets some low-level memory flags and it makes transferring back and forth really efficient. So I just mentioned it also just in case somebody runs into this. So all this is great. You can transfer memory back and forth. You can call built-in library functions or these collective operations like map. That gets you a huge amount of the way to doing useful work. Again, not everybody, but some functional programming people will tell you like map is all you need. If you need to do something other than a map, like you're living your life wrong. I guess maybe they'll also admit you need like CAR and CDR, like head and tail. But sometimes there's nothing for it. We have to write our own custom functions to run on the GPU. So these things, for historical reasons, are called kernels. That's why there's a corn emoji here, because the corn is covered with kernels. I was like really creative when I came up with this. So the next thing we're going to talk about is actually how we write and create our own kernels that are compiled for us by Julia and run on the GPU. So there's some additional challenges that come with this. I know it's like probably a kind of a broken record of like, you want to do this, but it's really painful. So we have to make efficient use of the GPU hardware, which is non-intuitive because we're mostly used to programming CPUs. We don't have the entire Julia language available to us. There is a restricted subset. And for many operations, it's really not that obvious how to translate what we want to do into something that's performant on the GPU. So obviously, if you can just write your thing as a matrix multiplication, you're good. Or if it's something that like could reasonably look like a matrix multiplication, it's not so bad. But for other things, like for example, our alias table that we saw in the state vector simulation yesterday, if anybody wants a reference, there is a published efficient GPU algorithm for how to construct such an alias table, and it really looks nothing like the CPU algorithm. It's really not intuitive. So there's whole people in CS departments who like make their whole career of finding these sort of efficient GPU implementations for stuff that everybody has known how to do on the CPU for like decades and decades. So these functions that we are going to execute in a super parallel fashion are called kernels. I guess another way to think of it is like my beautiful corn emoji up here. We have one kernel that's executing many, many, many times on different input data. So in the matrix multiplication case, that would be like, you know, one specific row times one specific column. And even within there, there's more parallelism we can find. But the actual kernel is multiplying and summing up just one row times one column. Or another example would be like if we do map, then the actual kernel for that is just applying the function that we're mapping to like one specific element of the array or like one subset. And so we can write some, as I said, restricted subset of Julia within there. And then when we actually write this, CUDA.jl and its backend GPU compiler.jl will handle translating this and compiling it with LLVM to the underlying instruction set that the GPU has, which is different than what's normally available to us on the CPU, which is why we can't use all of Julia. And of course, all of the higher level functions we were talking about before, like map, or even stuff like addition are actually implemented behind the scenes as these kernels. And happily or not for us, we do already have a bunch of these written for you, so maybe you don't actually need to worry about this, but we're going to focus a little bit on how we actually write these ourselves. And I'm going to take some water. Okay, so now we kind of have to get into a little bit more detail. This is also pretty CUDA specific, so I apologize. So when we look at one of these streaming multiprocessors, I got to get up and do some more drawing. So what is this actually made of and what's it doing? I'm going to completely dry out. More Stefan's markers here. Ugh. So from the point of view as you as the programmer, there are thousands and thousands of little workers on this GPU, but they come in what are called like these little groups called warps. So, and these warps are groups of 32 workers. So warp, which is made out of 32 threads. So is anybody here like a fabric arts person? Just me? All right, cool. So in case the reason for this name is not obvious, if you are like weaving cloth, like in a t-shirt, if you set up a loom, you have a group of threads going from the top to the bottom. That's called a warp. And then the thread you bring through the sides, like to make fabric, is the weft. So some dork like me named this. But the reason it's called a warp is that it's a group of threads. It's not like related to the warped tour or anything. So what actually happens on the device is we send like, some function, okay? And this thing actually has a bunch of instructions. It has instruction F1, F2, F3, and F4, let's say. So in the ideal scenario, what happens is every single thread in the warp executes F1, and I'm about to get really tired of drawing these squares. And then, okay, they say, all right, everybody finished? Pause. Let's go. Then they execute F2. And I'm already like not going to draw these. Okay, everybody finished F2? Great, let's keep moving. F3. They finish F3, and then same, they move in lockstep, finishing F4. They're done the function. Okay. This is probably hard to see for you guys, I'm guessing. Okay. So now they're done, and they finished executing F on whatever piece of work they were given, and they phone home to the scheduler on the GPU, and they say, hey, we're ready to pick up some new work. And then they pick up a new chunk of the array, and they start the process over again. They do F1 all together. Okay, we're done. F2 all together. Done. And then they get to the bottom, and they finish, and they pick up a new chunk of work. So again, in the matrix multiplication example, this would be like they process row 10 of A and column 12 of B. Finish. Okay, now we pick row 5 of A and column 25 of B. So it's kind of out of order. Finish, and then they pick up a new piece of work in the schedule. So this is where the super fast parallel performance of the GPU comes from. The fact that these warps are executing sort of 32 pieces of work together in lockstep, and that there's actually many hundreds of these doing the same thing all at once. So again, in like the weaving example, of course, in like a real loom, when you're making a t-shirt or whatever, and they don't directly weave a t-shirt, but when they make a big piece of cloth, they don't just have 32 threads, right? Like if you imagine a loom in your mind, they have many thousands of threads, and they all work together as the shuttle goes back and forth and weaves the cloth through them. So that's sort of by analogy where this comes from. The actual mechanics of how a loom works past this point don't really map very well, but it's maybe like a little intuitive. So the challenge for us when we write a kernel that's going to work on this is to make sure that in our function that all of these 32 guys at one moment can execute F1 without somebody deciding like, I'm a rebel, I'm going to do something different. So This works great and is extremely efficient as long as everyone, again, we'll get to some of the complexities here, is doing the same thing. But the second one guy decides like, oh, you know what? I don't want to listen. Like, I'm going to do my own thing. Then all the advantages go away because I shall use the red for this to show like it's really bad. Now the schedule really has a problem if you know some of the threads are doing something different because it has to execute thread 0, F1. Okay, he's done. Now thread 1 gets to go on F1. Done. F1 goes on thread 3. So the parallelism is completely lost. And so you lose all the advantage of using this theoretically faster hardware, and life is really horrible, and you feel sad. Or maybe it's good because you're like, okay, I'm just going to quit doing this. So from our perspective, at one time, we actually can control, this is like also where this analogy gets really annoying. Usually we're actually controlling multiple works in what's called a group. This stuff is also really frustrating because there's like 40 million new jargon terms you're going to have to learn immediately, for which I apologize. So in practice, what happens is we actually have a group that is composed of, in this case, I made it small because I am really bad at drawing. We can have a group that's made out of 2 warps. So warp 1 and warp. And this all lives together in a group or a block. I'll call it a block, I guess, for simplicity. Cool. And so normally we don't directly deal with the index of a thread in a warp. Rather, from my kernel's perspective, so from this perspective of the function I'm running, I can see the index of each thread in my block. So this one would be like thread 0. This would be thread 31. This would be 32. And then over here would be 63. And the block could be bigger than this. So I could make it like 128 threads or 512 threads. I think the maximum on current CUDAs is 1024. They've changed it before. And when my kernel is launched, a single block will pick, some segment of the total amount of work that I tell the GPU I need to run, and then I can do stuff with information about the index of each thread and then the total index of my block. So that gives me info about, where in my array am I? Like, am I here? Or am I here? What's going on? And then also, it can give me information for each thread about where the so-called like warp boundary is. So, and again, I'm really sorry that we're kind of having to go at 1,000,000 miles an hour here. When we say that these have to step through together, that's true on the warp basis. So if it turns out that these ones are doing something different than these ones, that's fine. As long as these ones are all doing the same thing with the guys in their own work. So we have to be careful when we write our kernels that we ensure that all of the operations we're doing are so-called like warp aligned. So that, again, these ones all do the same thing, or these all do the same thing. And in practice, this is such a pain in the ass to do that NVIDIA has actually started violating this rule, and they made it a lot easier to write code that doesn't do this, which is going to make my lesson a little bit more complicated. But the short story is, if you can write code that obeys the rule that everything in a warp should be doing the same stuff, you'll find it much easier to write code that's GPU performant. But that's also where a lot of the challenge comes from, because you can probably see looking at this that it's really easy to do it wrong. And I also drew this way because I'm lazy and bad at drawing. But here I've sort of implied that all of the blocks, effectively it's a 1D structure. But actually, the blocks can have 3 indices in a 3D grid. So depending on, what the problem is you're doing, like, for example, if you're doing a weather simulation, and like, I guess we live in a 3D universe, so it makes sense. Like if you're simulating the atmosphere, you could have blocks, like some of them are moving in the X direction, and some are in the Y direction, and some are in the Z direction. And then from there, which cell in the atmosphere you're modeling in this finite element simulation. So there's a huge amount of complexity here that allows you to write a very performant and flexible GPU code, but it's also a huge problem because it's very hard to reason about. Oh, there's another question.
What do you mean by doing all the same thing?
Okay, so yeah, it would help to have an example here. So for example, if let's say I have some input array here, and I'm running out of colors. So let's say F1 for most of these is add 2 to the element, right? So these are all doing the same thing. But then I wrote some check in my code that says, hey, if my thread index is 31, we're not going to add 2. We're going to multiply by 2. This can create what's called warp divergence, which sounds cool, but is kind of a problem. Where because this one thread is not obeying the collective rule, every single thread has to be scheduled individually, and so you lose the performance benefit. So in fact, NVIDIA has a bunch of very, very smart compiler engineers who work really hard to protect you from doing this. But it can be easy to write code something like this, where you have one thread that's doing something very different from the others. Another example that can often give rise to this is you have an if-else condition. So if my thread index is odd, I don't know, take the sign of my thing, and if it's even, add 2. Okay, that's kind of stupid because I just made it up. But that can be the kind of situation where some threads are doing, they're going left and the other threads are going right. And the only way the scheduler has to deal with this is to schedule them individually, because it can't predict that every single thread is going to step through the function block in a warp-aligned way. Does that make sense? Okay. There's another question.
Is it faster? Let's say you're doing the same process all the way through the entire block, so you can use both warp 1 and warp 2.
Yeah.
Is it faster in this instance to have instead of 4 Fs here, just have 2 Fs that go through the block? Does the process of going to the next thread, is that take longer than just
So the annoying answer is it depends. So there's always a balance between having enough blocks to fully saturate the device versus giving each block enough work to do that it actually is able to efficiently run stuff. So by that I mean for example, as we'll see, there's a memory cost associated with reading memory into each thread. So if you can do one read for the entire block and then do a huge amount of work, and then for example, another read, that's usually much more efficient than doing run read and a really small amount of work and then moving on to the next block.
Yeah.
But it's hard to reason about it in advance. So it's hard to give people good general guidance, which I'm sorry about. Other questions? Yes.
How do you decide on, is this length of the warp fixed, or when you write your kernel, you can decide?
So the length of the warp is fixed by the hardware designer.
Okay.
But then the size of the block is flexible. And so for various reasons, usually the best choice is to have it be a power of 2, usually bigger than 32. But in theory, if you were crazy, you could be like, I'm going to make my block size 513. If you do this, you're almost certainly going to have warp divergence, but you could do it if you wanted to. But for example, if you look at NVIDIA's benchmarks for some of the libraries, you'll see that the flops, so the performance rate, is really spiky at problem size that's a power of 2. And the reason is that it's usually the most efficient problem size for these sort of block scheduling. If your problem doesn't fit into a direct power of 2, that's usually fine, even if it's an integer times the power of 2. There's also a huge amount of sort of sorcery in figuring out what is the optimal block size. Like if here I drew it as 64, again, because I'm lazy. But it could well be like 64, 128, 512, or 1024. Which one is best? It depends. So sometimes you can reason in advance. For example, if each block has to load a lot of memory, then usually a smaller block size is better. Or if there's very little memory reading you have to do, but a lot of computation, then maybe a bigger block size makes more sense. But again, it's kind of hard to give general guidance because usually the correct answer is just try some different ones and benchmark it. Also, again, I think this has become less relevant in recent years because NVIDIA especially, but also AMD, have poured a lot of money into making the driver substantially better and the runtime substantially better. So this is less important than it used to be, which I guess it's good that they make like $1 bajillion selling hardware. It turns out they can hire like really smart hardware engineers. So thank you, anybody watching this recording who works in NVIDIA hardware. We love you.
Send us free GPUs.
Okay. That was a lot of talking. So let's actually look at a CUDA kernel. So further down here, we have my thing, like my first CUDA kernel. So in theory, we write this exactly the same way we would write a Julia function, but we have some new technology available to us. So we can see the thread index. So that's the index of each thread in the block. And then the block index, which is, you know, which block in the total grid am I? And so from this information, you can figure out, you know, your sort of global position in like some array like A or B over there. And then here I've used a very special macro, QPrintln, to print out some beautiful information about our threads. So again, normally you wouldn't print stuff from a kernel, but it can be useful for debugging purposes. So we can launch this on the GPU that Google made available to us using the @CUDA macro. There's a huge amount of macros running around here. And when we do this, so I create a CUDA array of size 512, and I can use the CUDA macro to launch this with 64 threads. And then from there, can, you know, knowing that there's going to be 64 threads per block, I can figure out the appropriate number of blocks. I kind of cheated here because I made 512 evenly divisible by 64. That's the kind of thing you can do when you are making the notebook. But often in practice, it's not so simple. And then I can just launch this on my CUDA array. And we can see the output. So one thing we can notice immediately is that it appears that the first block to run, I'm going to like really have to scroll here. Oh, Jesus. Is not 1. So one thing that we also have to be careful about is that the blocks are scheduled completely out of order. So it's generally pretty unwise to have the execution within the block depend on a previous block having executed. There are exceptions to this, but this is like a pretty advanced topic. And so you're never guaranteed anything about the order in which the blocks are scheduled in. So you need to make sure, again, at a sort of the initial level, that they don't depend, like that block 4 cannot depend on block 3 already having run. And so all of these guys printed themselves out. And one sort of nice thing about the macro is that it prevents these strings from overlapping on top of each other. But in fact, all of these were running simultaneously on this GPU that we were given by Google. One thing that's really nice also is that so things like arrays that are allocated off a heap, you have to copy them into the GPU memory, but things that are stack allocated like tuples, regular numbers, or static arrays can be just accessed directly from the CUDA kernel. So if I run this on a static array, I can again see that in fact here in this case I only have 1 block, and then I can see all the threads executing. This can be really useful if you have like really small arrays or something. You can put them in the form of a tuple, and you can save yourself some memory transfer costs. Just something to consider. Another thing that's really nice about this Julia paradigm for programming these devices is that we can use dispatch on the GPU, which is kind of crazy. So again, for the folks who've ever had to do kernel programming in C, you end up writing like kernel FP32 or like kernel FP64, and you have a different version of your function for every type that you want to call. And in Julia on the device, you don't have to do this. So you can write very specific versions for like a specific data type if you have a certain optimization you want to do, or you can write a super generic one as a fallback. So here, again, just for illustrative purposes, I've written two kernels, one that takes a float 32 and one that takes a float 16 array. And you'll notice that the array type here is actually different than the CuArray that we saw earlier. So why is that? So when these arrays, oh my gosh, no, don't disconnect me. Okay. When these arrays are run on the kernel, they're actually transformed into a special sort of like kernel only type that is really restricted in the functions it supports. But for that reason, it's actually possible for the GPU compiler to compile it into something that the internal like NVIDIA instruction set can understand. So if you have like some custom struct that you want to use in kernels, you can definitely do that, but you just need to make sure that you have like a kernel only version of it that only uses the very restrictive set of functionality that's available in kernels. So what are some examples of that? You can't allocate memory, except with some small exceptions, in the kernel. So I can't create like a new array in this kernel. That will usually completely blow up the device. Except in these very special macros, I can't create strings because they're arbitrary length. I can't throw errors. So if you try and throw an error, you'll get a very, very angry message from LLVM. I can't have type instability, and I also can't have things that are what we would say are not bits types in Julia. So this thing, all of its member fields have to have a specific type that's like has a finite number of bits that's known at compile time. So we know the size of float 32 at compile time. It's 32 bits, really shocking. And then from there and the length of the array, we know exactly how much memory this thing is going to use. But what we can't do is have the element type here be some element type whose bit count is not known at compile time, which is the case for string or like big int, or I don't know. I'm like now blanking on non-bits types. Or any, for example. You can't pass a array of any's here because we don't know the size of those at compile time. And this might not sound super restrictive, but you can quickly run into problems with it. So I just bring it up for those of you who like really want to pass your own structs. And I made the output here a little goofy, but you can see that it dispatched this float 32 array to my beautiful kernel that's float 32 only. And then for float 16, which is half the width, it's dispatched into the other kernel, which is slender. Again, this is kind of a goofy example, but it shows that you're able to dispatch to specific device kernels based on the input types, which is kind of cool. And Julia will compile all of them for you with LLVM, which is also quite awesome. As I mentioned to someone during the break, the downside of being able to do this is that currently we cannot precompile these kernels. So every time you like start a new Julia session, your kernels have to be compiled anew. That can be kind of painful if your overall workflow doesn't run for very long, but it's also okay if you're doing like some HPC job that takes 3 weeks. So I guess it just sort of depends on the scenario. And for this reason, also like the first time you call map on a CUDA array or something, it's probably gonna be really slow. And then subsequent calls should be faster because it's precompiling. So then in this next little section, I tried to create some examples of warp divergence, and also kind of shows you some more of the stuff that you can actually use on the GPU. One thing I forgot to mention earlier is that CUDA kernels always have to return nothing. So you can't return scalars from these. They always got to return nothing, which means if you need to output something from whatever kernel it is, you need to have some sort of output array allocated for that. So we'll see that more later. So here I have a really dumb function I wrote where I'm reading a flag in from this input array based on my thread ID. And then depending on the flag, I do something different in this for loop. I either add some weird number or multiply some stuff into this just number array. I kind of like this example also because it shows you that there is actually a lot of stuff that you have available on the GPU So you have the function sine, you have cosine, some other trig functions. You can generate random numbers. You got pi, our beloved pi, our best friend. So one thing that also is like kind of nice about doing this from Julia is you have a lot of these functions that you're maybe like used to using, and we have a lot of good piping where GPU compiler can take something like this and compile it efficiently to something that runs pretty well on the GPU. This, apart from like up here, and maybe this doesn't look too different from Julia functions we're used to writing, which again is not really the case in CUDA-C or C++. So we can try launching variations of this kernel with various values for R. So I just launched this with 64 threads. The block count is implicitly 1. And here I've set the flag to be all zeros. So if the flag is 0 for everybody, everyone should do the same thing, and there should be no warp divergence. And we can indeed look at that and kind of check by using the inbuilt CUDA profiler. So this is also something that's really nice in the CUDA.jl formalism. We can just instantly profile our code and say like, okay, like where am I spending my time? Is it, launching kernels, actually running stuff? So you get sort of two tables, one from the CPU's perspective, where did I spend time? And then from the GPU's perspective, what kernels was I running and for how long? So here we can see that, again, we have like about 66 microseconds to actually launch the kernel, which is about what I said earlier. It's like order of magnitude. And then the GPU was actually busy executing this stupid thing for about 3 milliseconds, which is bigger than this. So we must have made good use of the device, right? And that, I guess, kind of makes sense because this didn't actually end up diverging at all. Okay. So then if I create a set of flags that are warp aligned, so the first 32 are all 0 and the second 32 are all 1, that's also fine. And when I run this, I again see that it's actually like pretty comparable. It's 1.6 milliseconds. If I make everything all ones, okay, also great. We see again something relatively reasonable. And then if I just start generating like effectively like random crap, like I make some just random ints. Now we see that the kernel runtime has about doubled. And this is again kind of a dumb example because I used this analogy, I guess, with somebody else yesterday, but you might have heard this story that like when they have to design trash cans at Yosemite National Park, it's like really kind of a problem because the stupidest human is dumber than the smartest bear. So the bears can like open the trash can and get to the food, and the humans can't necessarily open it to throw away their food. And so that's exactly in this sort of contrived example what I experience here, where the stupidest notebook developer is not good enough at coming up with a good diverging example that the really smart people who work for NVIDIA can't defeat with their compiler technology. So they can look at my kernel and they're like, you moron. Don't do that. Like, we're gonna, modify this in a way where the results are still correct, but we protected you for something really stupid you were trying to do for unknown reasons, but probably because you were dumb. And it's like, yeah, well, yes, I am dumb. But I also wanted to, have a nice example of how bad warp diversions can be, but they put so much effort into making this hard to trigger that I don't have as nice of an example as I might like. So I'm sorry about that. I guess if I were really good at coming up with these, I would already be working there as a compiler engineer. So what's up, Michael?
Let's say I write some code that
Yeah.
I just write code for like normal arrays.
Yes.
Like something that uses BLAS a lot, like maybe like a Krylov,
Yes.
exponentiation, like that. So I write it for regular arrays, and then I just call it, and I just give it like these like GPU arrays. And I've done that, and sometimes it's faster, but like I don't know what's going on at all. It's just sort of a black box. Is this the best tool, or the only tool, or is this a tool where I can say I call this profiler, and that tells me like, is it actually running on the GPU? Like, what is it actually doing?
Yeah, so this is a really good like lightweight way to just figure out like what the hell is the GPU doing. Because it'll also give you information like we talked about earlier. Launching kernels itself is slow. Like if I, like the same as calling my friend like 100 times is slow versus just calling him once. So this will give you information like, yo, you're launching like 40 million kernels. and you're like, oh no, I shouldn't be doing that. And then I didn't include that here, but it'll also include things like memory transfers. So, you might say like, oh, I'm spending all my time transferring memory back and forth and not actually doing any useful work. Well, that's not very good. How can I optimize that? And then the device side will just say like which kernels took the most time. So it'll at least give you some idea of like where to look. And this profiler is great because it just ships with CUDA.jl and you don't have to do anything. Then NVIDIA has their own 2 other profilers that are external. And I always get them mixed up. There's Nsight Systems, which allows you to take a trace of the entire program, and it'll show you like when was the GPU used, how intensively, like what utilization was it being used at. And you can even, this is also very nice, I guess, you can press a button that's like, please tell me what to do. And it'll be like, here's my suggestions to how to make your code a little bit faster. Again, this is like generated by a machine, so I guess it might or might not be good, but it can give you some hints of where to look. And then they have a kernel-specific profiler whose name, I think Nsight Compute. They love giving this stuff like bizarre names. Sorry, NVIDIA. And that will give you kernel-level profiling, so you can inspect like what each thread is doing, and it'll warn you like, yo, you're having really bad warp divergence, or your block is a really bad size, or something like that. So I guess like the generally recommended path is to start with just this one that doesn't require you to download anything, and then try Nsight Systems that will warn you, like you're not utilizing the GPU very effectively, and then you can use the kernel-based one if you really are writing custom kernels. And this is also all like developed in the CUDA.jl documentation. For the other GPU libraries, like I think for AMD, we don't wrap the profiler as well. So this is also the reason I chose to focus on CUDA, is like it's the most mature for us. And I think the same is true for Metal. So on those other platforms, it's not nearly as developed and you're kind of on your own. Again, sorry, AMD. I guess also since this is being recorded, I want to mention, I don't think the NVIDIA compiler people are like grizzly bears in Yosemite. They're very nice people. Yes.
If you go up to the example you had, the function. So, okay, so this is probably a very nice question. So you said these functions don't return anything?
Yeah.
So I was trying to see how are we getting the answer back?
Yeah, so indeed, this example is just to show like the divergence. So the answer is we aren't.
Okay.
But if I were like doing this for real, I would have like out array.
And you'll store it.
Yeah, and then I would do like out array, like, oh my God, I'm doing this live, so this is like really nerve-wracking. Like plus block index.x times block dimension. So that block dimension tells you how many threads are in each block, and this gives you effectively your global index. This is like equal to A.
Yeah. Okay.
Does that answer your question?
Yeah.
And then there's another question.
Yeah, just as a follow-up to that. So does it mean anytime you want to access that array, you just keep calling the GPU?
Yeah, so if it's indeed, if it's living in GPU memory, then to access it, you're always having to do this super high latency, like effectively like phone a friend situation.
Is there a way to transfer it to CPU, like to like the RAM, like or...
Yeah, so there's this package that we have in Julia called adapt that will let you like move the memory back and forth. Or you can put the memory in this sort of like unified memory that we talked about earlier, where it's now visible from both sides, and then CUDA handles moving it back and forth for you. So it's kind of up to you which you want to do. And one thing that also is kind of nice about the CUDA paradigm is that because the GPU can be doing multiple things at once, while a kernel is executing, you can be transferring new memory over as long as it's not full. So there's a whole like art to sort of like layering these things on top of each other, such that like as thing A finishes, thing B is moving over, and then a new kernel launches with thing B. And so the device is always being used and always transferring memory in an efficient way. But that's, of course, like easy to say and harder to do. So, okay. I'm going to try and keep moving because I don't want to keep people here all night. Okay. So when we're actually like programming arrays inside kernels, the situation is actually even more fraught. So when one of these warps is executing, there's actually 3 types of memory it has access to. So there's the global memory, which is just the on-device RAM. So that's what we've been dealing with basically the entire lesson. That's memory on the device that is visible to every single thread, every single multiprocessor, and anyone can access it. And it's the largest and slowest of all the memory on the device, which doesn't sound great. Then there's this so-called like local memory, which holds locally defined variables. So like, for example, if every thread says like, I have an integer and it's 5, that lives in the local memory. And that's generally very small. It's just big enough to hold like some small integers or also like the index information, stuff like that. And then there's something that's very unique to the GPU. It's this so-called shared memory, which is, and this will really shock you, it's shared among all of the threads in this 32-thread warp. So this memory is kind of exciting, but also dangerous because it allows threads to communicate with one another. So this cartoon I drew here actually is a little inaccurate because each of these warps has a little pool of memory right here that's actually located very close to them on the device. And all of the threads, and only the threads in this warp, can see into this block of memory, and it allows them to exchange information. So effectively, like, these threads can use this small and very fast piece of memory to pass notes to one another. And they can do this in a way that avoids warp divergence, but allows them to collectively do stuff that's useful. So for example, the threads can fill up this little memory here, and then they can all vote. They can say like, okay, like, you know, I do something and I get 1, and I got 1, and I got 0, and I got 1, 1, 1, 0, 1. Okay, so everybody filled this up with zeros and ones. Let's all vote. Did we get majority zeros or majority ones? Okay, now that we voted, what do we do next? And so then they can make a collective decision without causing warp divergence. Or they can add up all of these and then store the result in memory. Oh, yes.
So because of this shared memory, you
Yeah.
could run potentially embarrassingly parallel multi-threaded processes where each warp votes amongst itself, but the
So on the warp level, it's not embarrassingly parallel. It's just regularly parallel because it's small. But yes, so yeah, so you can effectively think of it a little bit more as like, this is sort of a shared scratch space where everyone can communicate with each other and make decisions collectively.
Right, no, but I mean different warps don't communicate.
Different warps, yeah, so this warp, this guy can't see into here.
Right, okay.
But everybody in here can see into this and they can access it very quickly.
Okay.
And so a huge amount of writing these efficient GPU kernels is finding a way to use this effectively without filling it up too much. Again, easier said than done. And there's another question.
This also work as like a form of triple redundancy, or it's kind of different thing.
Sorry, could you repeat that?
It can like also work as like a form of triple redundancy, or that's a different thing entirely.
I think that's a different thing, yeah. Okay. So when we're programming with this in CUDA, and this is again like kind of a, I guess, advanced topic, from the point of view of the kernel, we just have some, in each thread, some shared array, which each thread in the warp sees, and we can make it either a static size that's known at compile time or a dynamic size that we specify when we launch the kernel. And then every single thread in the warp can see this. And so they can all work together based on, you know, like whatever we tell them to do. And then we can call this sync threads function, which we almost always want to do when we're working with the shared memory. So what that says is, okay, you know, each thread here is like doing some stuff. Like you're operating here, you're doing something here, you're doing something here. And when we call sync threads, we say, okay, you know, everybody done, right? Everybody's done moving their memory. Everyone has agreed on what the shared memory is doing. All right, now we're ready to proceed and, you know, use the results. So there's a couple different functions that we can use in this like situation after we synced. We can, as I said, vote. We can add stuff up. If you're interested in what all of these are, there's some pretty good documentation about it in the NVIDIA docs that I'll link later. And this is just a quick example of how you can use this to actually in place reverse an array using the shared memory. And again, this is like kind of, I guess, an advanced topic, so I'll breeze past it a little bit also because we're going relatively later than I thought. And I guess the last thing I want to mention, sort of for the CUDA section, is that the order in which we access array elements is really, really important on the GPU. It can have very large performance impacts. So the reason for this is that, as we just said, this RAM that's accessible to every single thread is really big, but it's also slow. And so we want to make sure we're doing reads or writes to and from this thing, from each thread, in the most efficient way possible. And there's very hardware specific, I guess, ways to handle this. In particular, like when we read a single element from an array, under the hood, you're usually never reading just a single element. In fact, you read like, again, it depends on the underlying data size, but you might be reading 8 elements, but most of them are hidden from you. So if you can write your kernel in such a way that you directly access all those 8 elements at once, you can save yourself a huge amount of time. And this, again, is like, there's a lot of complexity here, and it really depends on the specific GPU you're using, like the so-called word size, and then the specific access pattern you have, but I just wanted to mention it. Because if you read the programming guide, they talk a lot about the so-called coalesced memory access. So what they mean by this is when you read from memory, you want to make sure all the threads read in such a way that you have to load the minimum number of words. And this has a very, very big impact on the performance. So when they say this, they mean you want to write your kernel in such a way that like one thread block loads like this chunk, which is relatively small, and only this chunk, and does so in a way that aligns with the warp boundary. And once you've done that, then there's like a whole sort of literature on how you can load these words into the shared memory and access it very efficiently in order to do whatever computation it is. So why am I mentioning this when it sounds like a huge pain in the butt? Well, NVIDIA has a nice performance chart where they ran on like a V100, so actually a pretty old GPU. I think the V100s are like 10 years old. So the actual memory bandwidth they get for matrix multiplication, if you do something naive, like I showed here, you get about 13 gigabytes per second of transfer. And if you carefully read memory from the global GPU RAM into shared memory in a sort of warp-aligned way that's coalesced, your memory bandwidth is 10 times faster, which is a pretty dramatic difference. So if if your whatever kernel you're writing doesn't need to read a lot of memory, you can be like, okay, I don't give a shit. I probably shouldn't swear on this, sorry. But if you are dealing a lot with like, loading memory, doing operations on it, writing it back, like for example, if you're doing a state vector or tensor network computation, this can be really, really important. And then finally, there's like some more optimizations you can do to avoid having multiple threads try and read from the same location in memory at the same time. And if you really push it, even on this pretty old and crappy card, you can get up to 200 gigabytes per second, which is really impressive. So this is the kind of thing, I guess, like you can worry about, you can cross that bridge when you get there, but it's just worth keeping in mind that, if you're like me and you write a kernel and you're like, oh my God, I wrote my kernel and it's correct. Wow. And then you look at your performance and you're like, wow, this is crap. Again, that often happens to me like basically every day. In a way, it's kind of a heartening message that there are known ways, if your operations are memory intensive, that you can boost your performance very strongly. And also to go back to the question Michael asked, this is also something that the profiler from NVIDIA can help you with. If you run analysis on your kernels, it'll throw up like a big red triangle icon and say your memory access pattern is bad. And here's some suggestions for how to fix it. And then you can read the CUDA.c programming guide and say like, I don't really understand how to fix this. That's my experience. But there's now more and more guides, sort of, I guess, like how more effectively to do this. So I guess if you want to discuss this more, I don't want to like completely lose us in the weeds here. But just to mention that this can have a really big impact on your performance and you might have to worry about it at some point. And as I mentioned, there's like a pretty good profiler available just in the package itself. This also goes back to your question. So here's like a little bit more interesting of a trace of a program I ran that actually involves copies. So I'm copying a bunch of memory from the host, which is the CPU, to the device, and I'm doing it asynchronously, which is the default in CUDA.jl. So unsurprisingly, I'm spending a huge amount of time doing that. That's why it's in red. I'm being called out. And then I'm copying a bunch of memory back at the end. I'm launching kernels. You might see this like CUDA stream create stuff and be like, what the heck is that? I didn't create any streams. Like, who are these streams? So what's happening here is that when I launch the CUDA kernels in different threads, effectively there's like a GPU side thread that Julia is creating and managing for us. So operations within a single stream that's managed by a thread are done in order, but the streams execute out of order. So for example, if you have memory that has to be transferred for kernel A, you want to put it in the same stream or the same thread that kernel A will execute in, and CUDA guarantees that the kernel only starts to run after the memory transfer is finished. And then once I look at my device side activity, I'm spending a huge amount of time copying memory around because I wrote a really dumb, crappy kernel here. And then I spend some more time in these internal kernels that have been written for me. And then I'll just try and end this segment, and I promise we'll have a break in a second. Just with some more general tips and tricks that are like kind of CUDA specific. One big one is that the newer GPUs have these specific objects called tensor cores that are, I guess, like kind of as the name implies, they're really good for tensor contractions on pretty small objects. They handle a very restrictive set of types. These are why also the performance for machine learning applications on NVIDIA GPUs is really, really good because again, their entire life, all they think about is contracting tensors, but they're very specific, funky little tensors on really low precision floats. But the performance there can be 100 times better than on just the regular threads. So if you are able to use these at all possible, you should. Generally, lower precision on these devices is faster than higher precision, which is really kind of a pain for us as physicists because not only do we need 64-bit floats, but we need two of them because usually we have to deal with complex numbers. Also, just because this also happened to me recently, the Julia GPU ecosystem, and I'd say compared to others I used especially, is really powerful and there's a lot of things you can do with it. But sometimes your code is wrong because of an LLVM bug, and this actually happened to me twice this month. So sometimes you test your kernel and you're like, I think my kernel is right. I really can't find the bug. And the reason is that it's not your bug. It's LLVM. And the only way to really detect that is to just open an issue on the relevant GPU repo and be like, this doesn't make any sense. And if you're like me, you can throw a big tantrum, or you can leave a nice message being like, this really doesn't make any sense. Can somebody help me debug it? But just to keep in mind that you can sometimes run into crazy bugs that make no sense. And I think it happens substantially more frequently than CPU programming. One other thing to mention is that on these newer NVIDIA GPUs, support for doubles is provided via emulation algorithms that you can look into. And if you follow this beautiful link I included from lower precision floats, you can control how that's done. It can have correctness implications for some algorithms we want to run. The reason that this is the case is that basically the people like us who want to run things with support for doubles or complex doubles, we're 0.01% of the market for GPUs. The vast majority of people buying these cards want to do machine learning stuff where they're using real brain float 16s or sometimes even smaller types. They don't care about doubles. They've probably heard about doubles, but they don't want to hear about them again. They don't use them. Why would you ever use a double? You have to have something seriously wrong with you to ever use a double. So they continue to provide support for it via emulation. But it's just something to keep in mind, again, if you run into weird correctness bugs, that it might be related to the emulation you're doing. But I guess it's nice of them to still think of us. When they make these new cards, they still support us. The other thing that's also kind of nice is that CUDA.jl is now actually sort of a thin layer on top of the more independent library packages. So you can import only the ones you need. This is great because a lot of the libraries we need to use are really big. When you load cuBLAS, you actually end up doing a DL open on a shared object file, which is itself 500 megabytes. That's pretty expensive. So if you can avoid having to do that by only loading cuSolver or something, you should try and do so. So this allows you to reduce load times. One other thing is that a lot of the array methods we might need don't yet have an equivalent GPU implementation. You're welcome to add them or yell at us to add them by opening issues. And then finally, I'll also mention here that there's like the type stability in the GPU code is really, really important. You can have type unstable code that will not compile, or it can be very slow if the compiler helps you. So I guess that's the end.